Calculus AB 2018 AP exam question number 6. Okay, it says consider the differential equation. So this is a slope field type of equation problem. Okay, there's 3 parts to it. So let's go and we'll do each part individually here. So part A, I just reproduced the slope field over here. So this is what's going on here. They gave us, this is the slope field. And if you took all these different coordinates here, whatever they are, like at the point, this point here, 2, 0, and you plug 2, 0 in, you get a slope of 0. If you plug in the point over here, 1, 0, this is 0, 2, excuse me, you plug in the point 1, 0, you would get a slope that looks like about 1. Okay, and they do that through all these. So this is called a slope field. They use this slope function to produce all these little tangents. Okay. And it's hard to see here, but there is a family of curves. And the reason we get a family of curves, you can sort of see how the curves, if they follow these little tangents, would go through here. And there could be a curve down here someplace, and it gets steep here. And there looks like it could be a curve here that's almost horizontal. Okay, and let's get a little idea about that first. This is a more complicated function. So let's just take simple functions. Let's take these functions here. Y equals x squared plus 1, x squared plus 3, x squared minus 1 plus 7, x squared minus 5. Okay? They're all different functions. And if I was to take the derivative of every one of these, the derivative of each one is simply 2x. Okay? So if I didn't know which function I was talking about, and I drew a slope field with using the function, slope field function 2x, every one of these curves would be in there someplace. Okay, so if I was to integrate this, this is when you integrate, you get that plus c, you get the constant of integration. You don't know what the particular solution is, okay? You only know the general solution. And in order to find the particular solution, you need a point on the curve to actually figure out what c is. That's what they're having us do here, okay? So here they gave us this slope field here, and they want us to sketch the slope curves that go through the point 0, 2, the point 0, 2, okay? Well, that looks pretty straightforward, okay? It looks like, and make sure you better go through this point, so always start with this point. That's the only thing that is given to you here, fixed, okay? And so it looks like it's just a horizontal line, okay? And that's what you get for this one here. So that would be your slope field there. And make sure you go all the way to the ends, okay? This one over here, now it says do the same thing through the point 1, 0. Now, again, start with this point here, and you don't have to be accurate, but at least you have to sort of follow. So if I was to do it, I'd start here, and I'd go one way, and you sort of follow these little tangents, and it bends here, and it just sort of flattens out, okay? And then you come over here, and you see it follow these tangents, and it looks like the slope is 0 in here, and then it's just going to go along up here, okay? And then it's going to flatten out over here again too. So that's what you're going to do. That's the slope field. Now it doesn't have to be perfect like this one. It just has to go through this point and has to follow through these tangents. See, it's always kind of parallel. I'll show you here. I have a little sliding tangent I have on this curve here. This is a little sliding tangent. And anywhere I go along this curve here, you see the little tangent to the curve is always parallel to these little slope fields, no matter where I am, okay? And here, see here, slope is 0, and it just follows through in there, okay? All right, let's go to the next part of this question. That should be a pretty easy part, okay? The next part here says, again, here's this differential equation. It says, let f of x be a particular solution to the given differential equation with initial conditions. So in other words, it's saying that there's a point on this function. If I was to solve for this function, there's a point on this function 1, 0, okay? And then it says write the equation, the tangent line to the graph of f of x at x equals 1, okay? And then use this equation to approximate f of 0.7. So what we want to do, it's not very complicated. It says write the equation of a tangent line, and it's got to go through this point. Well, in order to write the equation of a line, you need a point and a slope. But we already have the point, and be careful how you do this. Remember, this is f of x. 1 is x, f of x is y, so 0 is y. There's our point. Okay, now here's our slope function that they gave us. So now I need the slope at this point. So I just plug in 1 for x and plug in 0 for y. And I get the slope at that point, 1, 0, is 4/3. Okay, so the next thing I have to do is write the equation of a tangent line. Now, as far as I'm concerned, the easiest way to write the equation of a tangent line is what we call point-slope form. Okay, most of you are used to y equals mx plus b. Point-slope form is the easiest and fastest, and actually it's the most useful because it takes less work. So you could say, I don't know the point-slope form of the equation. Well, you do. If you know the slope equation is change in y over change in x. Most people know that. I mean, if you've taken Algebra 1, you know slope is change in y over change in x. And if you simply multiply by change in x, so you move it up here to the left, okay, so this is the equation. It's change in x times the slope equals change in y. And of course, you got to know that change, delta means change, so change in x would be x minus x point. That's a change, see, minus. And change in y is y minus y point. This is the point-slope form of the equation of line. See, point is x point, y point, slope. So all I have to do is plug these three things in there. I plug in 1 for x, 0 for y, and 4/3 for the slope. Now you can write it this way too, but you might get a little confused because when I move the y, move this to the other side, it becomes positive, and then one of them is positive, one is negative. Don't worry about it. If you leave it in this form right here and then change it afterwards, I just plug in 4/3, plug in the point, whatever it is. If it's positive or negative, just plug it in for x of p, plug in the y coordinate for yp. Okay, so here's here's the equation of the tangent line. Okay, so there's the 4/3 minus 1. 1 is the x coordinate, 0 is the y coordinate, and there's my, and I just changed it to tangent, t for tangent, okay? And I like this terminology because I'm going to plug in the 0.7. It says now use this equation to approximate f of 0.7. In other words, if I could plug 0.7 into the function, which I don't have, okay, I'm going to plug it into the tangent line and use it as an approximation. So, and again, this form is very simple because if I plug in 0.7 for x, this is simply minus 0.3. Minus 0.3 times 4/3 is minus 0.4. Okay, that's all there is to this part. The last part says find the particular solution to the given differential equation with initial condition. Okay, so we want to know this. Remember, if it was the general equation, when I integrate this, I would get a plus c. That's the whole family of curves, okay? I want the particular solution, which means it's one particular curve, and I'll be able to find out c because I know the initial condition here, the 0.10. Okay, so here's how we have to do this. Very important. The first step is very important. We have to do is, we call it separate variables. So here's the differential equation. I just rewrote it over here. And the key step here is to separate variables. In other words, I want all the x's on one side and all the y's on the other side. Okay, no, not mixed. There's no x's over here. There's no y's over here. Okay, and again, I would always leave the dy right here, because you're never going to put it in the denominator. We don't integrate with dy or dx in the denominator. So leave the dy there and just move the dx up here. And then I just have to move this y term over to the other side. Okay? Any constants like a third, it doesn't matter. I could multiply by 3 and move it to the other side, or leave it on this side as 1/3. It makes no difference. Okay? That's up to you. That's your preference. So here I've separated my variables. Okay, now I'm going to clean this up a little bit because the next thing I'm going to do is integrate both sides, but I can't integrate it the way it is, or I don't see it the way it is. So I'm going to move it to the numerator, and this becomes y minus 2 to the minus 2 power in the numerator. So now when I integrate, I can use the power rules. Okay, so the integral, use the power rule, you add 1 and divide by that value. And then here I have x squared over 2. Don't forget, very important, to put your plus c. Now, if you notice, I only have one constant of integration. I integrated both sides so I could put a plus c1 here and a plus c2 here. But if I move c1 over to the other side, I'd get c1 plus c2. It's just some other constant. So it's acceptable, it's standard practice that you just put one constant And if you're always going to be solving for y most likely, so the chances are you want to put the plus c on the x side. Okay, so you do that. Okay, so right now I have the equation. It's not in a nice form right now, and this is the general solution. Okay, this is not the particular solution because I have a plus c. So what I could do right now, you don't have to do any more algebra. A lot of times if you start fooling around with algebra, you make mistakes and it gets more complicated. So I could just go ahead and write now, and I could go ahead and find c. So I'm going to take this expression right here. Now the only thing I did here to move it up here is y to the negative, to the minus 1 power, I just moved it to the denominator. So this becomes y to the minus 2 to the first power. And then the minus 1, I put the minus here. So as I moved it up, I made it a little cleaner. And of course, 3 times 2 is 6. Okay, so now I'm going to plug in 1 for x and 0 for y. And I'm doing that right here. And I just do this arithmetic here, and I get c is equal to 1/3. Okay, so you have to just clean up this arithmetic over here. All right, now this is the key thing, is wherever I substituted into 1, 0, this is where I got to plug back in for the constant c. So this expression is exactly the same, just take c out and put what it's equal to. C was 1/3, plug it in here. Okay, now the only thing I have left to do is to solve for y. You may struggle with this a little bit. Algebra seems to be the biggest problem for most people in calculus. So I want the y in the numerator, so I need to take the reciprocal of both sides. I can't do it the way it is now because it's a sum of 2 fractions. So I got to combine this into 1 fraction. And then basically I can use property proportions. And so I can take the reciprocals of both sides. And I move the negative to the other side. Okay? And then I just went ahead and added 2. So here is the particular solution. So if I differentiated this right here, if I took the derivative, I'd get back to here. Okay, and it is the particular solution that satisfies this 0.10. Okay. Now let me just give you some visuals to give you a feeling for what's going on here. Okay, here is the particular solution we just found. So I just graphed it in here amongst the slope fields, and you can see how it follows all the little tangent lines. I can put the sliding tangent on here again and show you how as you go through, as you move along the curve here, this little purple bar or magenta bar is tangent to the curve as it moves, and you can see that it fits right in between all these little slopes, and it is parallel. It's not necessarily parallel to the mole because you see as we go up and down these different points, the slopes changing slightly, but if you notice, this slope of this magenta line would be between these 2 slopes here. So it's right in there. Okay, so it fits right in. That's one thing I wanted to show you a little bit. I want to show you the family of curves. In other words, if I was to just if I separated variables and integrated both sides and had plus c, and then I could plug in a whole bunch of different kinds of points, and I would get different curves. Okay, and you can see each of these curves follows all little tangents. This green line here is sort of flat all the way through. The red line, it follows the tangents, but it bends down a little bit. And then as I get further and further down, the curve bends further, but it's still, each one follows all the tangent lines as it goes through. So these are all particular solutions going through different points. The black one is the one that went through the 0.10. This one might go through the 0.11. This one might go through the point, whatever. It could go through the point down here of, 0 minus 2, for instance. Okay, so those are all our little tangents. Let me show you something about the part B here. I think this is, you don't really need to know this, but I think it's nice to see what's going on and what they're doing here, okay? What they had us do, they had us draw the tangent line at the 0.10. So here the black curve is the actual particular solution. What we really want to do, what they want us to do is find f of 0.7. We wanted to plug 0.7 into the function, into the black curve. Well, we didn't know the black curve, and maybe we couldn't find this function. It might be very difficult to find, okay? Or it might be very difficult to do the calculation. So if we couldn't find that function, what they say to do is they say, well, let's go close by here. So we know the 0.10 is on the curve, and they had you draw the tangent line. So that's what we did in part B. We drew the tangent line to that function at the 0.10, okay? And that was the tangent line right here. And so this red line is the tangent line. Okay. Now, if you notice in this region right here, okay, you can't tell the difference. The black curve and the red curve, or the actual function and the tangent line, they're on top of each other. Okay, and they're very close to each other. So what they're having us do here, when we plug 0.7, if we couldn't plug it into the function, they say, well, plug it into the tangent line. And so if I plug it into the tangent line, you see, if you look at it, here's where an x is 0.7, this blue line here, this blue vertical line. If I plug it into the function or the tangent line, I can't tell the difference. Okay, so if you notice what happened is when I plugged 0.7 into the tangent line, I got minus 0.4. And then what I actually did is after I found the function in part C, this was our function, remember, I plugged 0.7 in there. Now the arithmetic's a little uglier, but it's not a big deal. And then I found that to be minus 0.41. Now if you notice, these two values are very close. Okay, and this is a concept, and I just wanted you to see what they're doing. This is called local linear approximation. So if I want to find the value on some function, let's say like I said, some value here, 0.7, and I couldn't do that, I pick a value close to it where I can draw a tangent line. So it's close is local, linear tangent line, okay, approximation, use that tangent line to approximate the value. So this is called local linear approximation right here. And it's a way of estimating values on curves that I can't find the curve for. It's a good idea to understand these things sometimes. You don't really have to know that. Just follow the steps that they had you do, and you could have gotten that without really understanding what you're doing. But it's nice to understand. Okay. Now let's look at the points they gave us. Now if you notice, they gave us 2 points for the first part A, 1 point for each of these curves, 1 point for the curve through 0, 2, 1 point for the curve through 1, 0. But notice here they say curves must go through the indicated point. So if you don't hit that point, and you can't go way off and come back and hit it, okay? If you don't go through, so always start with those points. You don't get credit, and it must follow the slope lines, and it must extend to the boundary. So it must go all the way across the boundary, okay? Very easy, 2 points there. Okay. The next part of this question, you got 2 points. Equation of the tangent line. So right down here, all this little bit of work is only a little bit of arithmetic. The equation of the tangent line, you got 1 point and 1 point for the approximation. Okay. The last part is 5 points. Okay. Now, very important. You notice here, note 0 out of 5 points if no separation of variables. If you do not separate the variables in the first step, you will get 0 out of the 5 points. So you got to be very careful about that. And then there's another thing here too is once you get down to the step where you integrate, if you don't add the constant of integration, you can only get a maximum of 3 points out of 5. Okay? So what they basically gave you is 1 point for separating variables. But again, if you didn't, you're going to get 0 points for the whole question. Okay? 1 point for integrating each side. Okay, 1 point for the constant of integration and then finding C, and that's for the particular solution, and then 1 point for solving for Y. Okay, so that's the point value for this.